Başlattım. Finallerimiz 7 Haziran 20 Haziran arasındaki 2 haftadaymış. İşte şu aralıkta. Yani 3 Haziran son dersimiz olacak. Yaklaşık 1, 2, 3, 4, 5 yaklaşık değil 5 haftamız var bu haftayla beraber. İşte 1, 2, 3, 4, 5 haftalık konumuz var. Bir dakika arkadaşlar. Evet, şimdi geçen hafta küçük bir ödev vermiştim. Ödevimiz neydi? 3. soruydu arkadaşlar. Lowercase letter'ları uppercase letter'lara çeviren küçük bir program yazacaktık. Yapan bir Utku arkadaşınız vardı. Basitçe yapmaya çalışmıştı. Tekrar da bir mail almadım kendisinden. Şimdi cevabı açıyorum direkt. Cevabın üstünden anlatacağım size. Çünkü bu dersin konusu değil. Bu örneği sadece anlatmış olmak istiyorum. İşte data segmentin ayarlanması. Bu kısmı artık biliyorsunuz. Data segment zaten 100 geliyordu. Bu şu an gereksiz bir değişiklik. İsim diye bir değişken tanımlamış. Define byte keyword ile. İçerisinde büyüklü küçüklü bir isim var. Benim ismim. En sonuna da 0 eklemiş. Emulate dediğimiz zaman ismin yazıldığı yer bakın neresiymiş? 1023 H'tan itibaren ABBA boşluk ELMAS null. En sonunda 0'ı koymuşuz. Tamam. Şimdi şu da bitiş bizim return. Olması gereken düzgün return to operating system kısmı dedik. Bir döngümüz var. Döngü içerisinde karakterleri ekrana basacağız. Karakterleri ekrana basabilmek için ahenin içerisinde olması gerekiyordu. Hatırlayın. Interrupt'lardan onH ve ahenin içerisinde kombinasyonu teletype output'tu. Yani ekrana bir şey basmaydı. Neyi basıyordu? AL'yi ekrana basıyordu. Tamam mı? O yüzden ahenin içerisinde koyup devam ediyoruz. Döngüye giriyoruz. Döngümüz sonsuz döngü. Bakın unconditional jump'la yapılmış bir döngü. Yani bu içeri tarafta bir yerde birisi bitişe atlayacak. Tamam. Şimdi ekrana yazdıracağımız değişken isim, onun efektif adresini çözümlüyoruz. Ne ile? Load efektif adres komutuyla. Çözümledik. Bx'in içerisine yazdık load efektif adresle. Bize offset'ini verdi. Offset'ini parantez içine yazdık. Data segmenti de önüne koyuyor biliyorsunuz. Yazmazsanız da. AL'nin içerisine ilk karakteri koyduk. Bu başlangıcından itibaren byte'lık kadar kısmı AL'nin içerisine koydu. Sonra olay başlıyor. Ne diyoruz? 0 geldi mi? Yani son karakterimiz geldi mi? Nasıl anlıyoruz geldi mi gelmedi mi? AL'den yüklediğimiz karakterden 0'ı çıkartıyoruz. Sonuca bakıyoruz. Sonucumuz, daha doğrusu sonucumuz demeyelim de o işlemin yapıldıktan sonraki flaglere bakıyoruz. Sonuç bir yere kaydedilmiyor çünkü hatırlayın. JE'yi kullanmış. JE dediğimiz jump equal. Jump equal zero flag'e bakıyor. Zero flag 0 ise bitiriyor. Buraya giriyor. Bu döngü çalışmadan eğer 0 geldiği anda atlıyor. 0 gelmezse bir compare'i daha var. Şimdi sorumuz neydi? Lowercase'i uppercase'e çevirmekti. Bize bir ASCII table lazım. Evet, elimizde şöyle bir ASCII table var. Şuraya alayım. Birinci karşılaştırmamız 97 ile karşılaştırıyoruz. 97 ne? 97 decimal bu arada. Bakın sonunda hiçbir karakter yok. Harf yok. Hexadecimal değil. Decimal'a bakıyoruz. 97'miz küçük a. Karşılaştırıyoruz. 97 ile karşılaştırdık. Flag'leri set ettik. Ne diyor? Jump below. 97'den küçükse demeye çalışmış. 97'den küçükse şu tablonun sol tarafı komple. Yani burası. Zaten ya uppercase ya bir karakter. Hiçbir şey yapmayacağız. Yazdır kısmına atlayacağız. Yazdır kısmı şurası. Yazdır kısmı ne yapıyor? Interrupt tenhash'ı çağırıyor. Bu ekrana bir karakter basıyor. B-1 arttırıyor ve döngü başa dönüyor. B-1 arttırdığımız için yeni karakteri yükledik. Yeni karakter 0 mı değil mi baktık. 0 değilse bitişe gitmedik. Geldik 97 ile karşılaştırdık. Diyelim ki 97'den küçük değil. Yani şu tarafta bir şey. 97'den küçük değilse bir de 122'den büyük değilse diye bakmamız lazım. 122'den büyükse onunla da karşılaştırıp 122'den büyükse ne yapacağız? Parantezdir, şudur budur karakterler var. Bunları da direkt ekrana yazdıracağız. O yüzden direkt yazdır çağırdık büyükse. 97'den küçük değil, 122'den büyük değilse nedir? 97 ile 122 arasındadır. Yani küçük karakterlerdir. Lowercase'dir. O zaman ne yapacağız? Tek bir işlem var. 32 çıkartacağız. 97'den 32'yi çıkardığımız anda 65 olacak. Büyük A. İşte 109'dan 32 çıkardığımız anda 77 büyük M olacak. Bu programda böylece çalışacak. Mesela araya başka karakter bir şey atalım. Space'ten başka bir karakter olsun. İşte virgül, space, ünlem. Şöyle bir olsun. Bu sefer biraz hızlı çalıştıracağım. Virgülü de yazdırdı bakın. Ünlemi de yazdırdı. Gidip virgülü uppercase'e çevirmeye çalışmadı. Çünkü virgülün uppercase diye bir şey yok. Ünlemi uppercase'e çevirmeye çalışmadı. Ünlemin uppercase diye bir şey yok. Evet, geçen haftaki ödeviniz size verdiğim, bunu çözün dediğim ödeviniz buydu. Bu zaten şu an burada 3. örnek olarak duruyor. 7. haftanın 3. örneği. Bu niye Dojix yazıyor ya? Anladım. Sınavı geçtik, interrupt'ı geçtik, ASCII table'ı geçtik, 7. haftayı kapattık, 8. haftayı açtık. Evet. Hey my friends, today's topic is shifts. Shift left, shift arithmetic left, shift right, shift arithmetic right. There are 4 instructions. 2 of them is exactly same. That's why we are going to cover only 3 instructions. One of them is shift left, others are shift right and shift arithmetic right. Whenever we see a new instruction, remember we open help and 8086 instruction set and go to first instruction. What was that? It is shift left. Where is shift left? Shift left is here. Okay. Shift left has 2 parameters. One of them can be memory, the other can be immediate. One of them is register, the other is immediate. Other than immediate, it can get CL value. Bakın, this is predefined. You can't use CX, BX, BL, AL. It only accepts CL or immediate value. Let me write something. Put some value into AX like 1, 1, 1, 1, 0, 0, 0, 0 binary and use shift left command. Shift left AX, I use register immediate comment now. Immediate value will be, for example, 2. I'm going to shift this value, F0 value, 2 bit left. Okay. We are going to see what is happening right now. I want you to be careful because in theory lesson, these shift commands cannot accept bigger than 1. It only accepts 1. That's why this emulator shows us 1 in here. It split this 2 value into 2 and shows us 2 lines. For example, if I write 5 in here, it will divide it into 5. Because this is the actual usage of shift left. You can't use 5 in emulator in real. You have to use 1, 1, 1. Just never mind that because our emulator support writing some value other than 1. Okay. We put some value into AX. As you can see, we only use the AL part because we put 8-bit value. Now the value is F0. We are going to look at the values in here. This is our value F0. Okay, now let me put this in here. Okay. I'm going to shift this 1 bit to the left. Go back and shift. Please look at the here. When we shift 1 bit to the left, the most significant bit of AL goes into AH because I say shift AX. The complete AX value will be shifted to the left. I'm going to do that again. And the result is 3C0. 3C0 is the result of shifting 2 bit of AX. Okay, I'm going to change this. I'm going to shift AL, not the whole AX, but AL. Okay, we have F0 in here. I'm going to shift only AL. The first bit of this most significant bit of AL is not going to go up into AH. Be careful. As you can see, it is shifting to the left. The most significant bit is removed. 0 is coming from the right. 1 again. The result is C0. So it is important what you are shifting. Be careful. If I shift AX, it is using all of the register. If I use AL, it's only using AL. It is important. We can use CL and use CL in here. This is the same. The result is C0. Just know that. Okay, so what is the algorithm? What it is doing? The shift arithmetic left and shift logical left instructions perform the same operation. They shift the bits in the destination operand to the left. This is our 11110000 F0 register in AL. It's going to shift to the left. For each shift count, the most significant bit of the destination operand is shifted into carry flag. Let's see. We didn't look at the carry flag, but algorithm said that it drops into carry flag. Let me clear this CL usage and 3 times. Shift this 3 times and open the flags. Okay, we put F0. F0 is here. F0 is here. We are going to shift one by one. The first shift. When we shift AL, please look at the carry flag. Carry flag is set to 1. And the value is 1110000. Again, shift. Carry flag is again 1. The result is 11000. I'm going to shift again. Oh, we have 1 in here. Let's change this into something recognizable. Let me open again. Okay, we have 10101000. What is this? It is A8. I'm going to shift this 1010 into 3 times to the left. Shift left. I want you to carefully look at the carry flag. Carry flag is now 0. When I shift to left, the most significant bit dropped into carry flag. And the value is now this plus 0. As we can see, this is the previous value. It adds 0 at the end. Another shift. Please look at the carry flag. The first bit is now this. This 0 will drop into carry flag. And now carry flag is 0. Again, another shift, another bit 1 dropped into carry flag. So every time a shift occurs, the carry flag is updated. Be careful. The least significant bit is cleared, which means we are adding 0 from the right part of this register or memory. Let me put all ones here, and I want you to see the rightmost bit in here. Okay, we have FF in here, 1 1 1 1. When we shift 1 times, did you see a 0 comes from the right? Another shift, another 0 is come. Another shift, another 0 is come. So the result is F8. Okay, this is shift left. 0 bit inserted to the rightmost position. Shift all bits goes to the carry flag. Only affected flags are carry flag and overflow flag. If first operand keeps original sign, overflow flag is 0. Anyway, let's open the shift arithmetic left, which we say the same. As we can see, parameters are same. Arithmetic operand y left, the number of shifts set by operand 2, blah blah. As you can see, they are all same. So I'm going over to shift right. Okay, parameters are same. You can use memory or register with immediate or CL value. It shifts operand first operand to the right. Number of shift is set by operand 2. Shift all bits right. The bit that goes off is set to carry flag. 0 bit inserted to the leftmost position. Oops. Let me open that again. Shift right. This is the example we are covering. Let me open this zoom. Yep. Okay, we have a register. When you use shift right, the most significant bit is cleared, which means that enters zeros from the left. The least significant bit, which has information, will drop into carry flag. So let's change this, into shift right. and use some meaningful values. Okay, this is shift right. We are going to shift right AL and opens the char flag. We are going to shift right this value, the rightmost significant bit. This is the least significant bit. Will drop into char flag. 0 will be entered from here. Let's write it down in here. This is F5, as you can see in here. When I go single step, shift right by 1. Let me zoom in here. See the whole screen. Let me show you like this. Okay, the first bit drop into char flag and 0 will be entered through left. So the value is 0 1 1 1 1 0 1 0 0 1 1 1 1 0 1 0. Okay, this is a single step of shift right. Okay, another shift. This time the value is here. The rightmost significant bit is 0. This will drop into char flag, and char flag will be cleared. As you can see, it is cleared. It is dropped, and the 0 is come from the most significant bit of AL. That's it. This is shift right. 0 is coming from the left, least significant bit dropping into char flag. Okay, now we have shift arithmetic right. Let me explain this in here. Count the least significant bit, the most significant bit. The shift right instruction clears the most significant bit. The shift arithmetic right instruction set or clears the most significant bit corresponding to the sign. Shift arithmetic right means, for example, you have a value which is -1. What was the -1? -1 is, remember, FFH in 8-bit, FFFFH in 16-bit, FH in 4-bit, which means 1 1 1 1 goes like that. So you know that this is -1 by looking at the most significant bit of this register. The most significant bit is in here is the sign operand. Okay, if you look at the FF value as a signed value. So you have to keep those sign operand at that position in order to make arithmetic operations. So you know that you are working with signed values. You have to use shift arithmetic right in order to keep the most significant bit. Okay, let's use some value, for example, like this. I don't know what this is. Let's see what it is. What's it saying? Cannot be a count. This is not hexadecimal. This is binary. Okay, this value is CC. CC is, let me see, signed value is -56, -52. So I'm going to shift arithmetic right this value. Shift right, not shift right, shift arithmetic right this value. And open the flex, by the way. The right part is same. The rightmost bit, the least significant bit, whatever you call, is drop into char flag. But this time, whatever the first value is there, it is going to keep entering the first bit. So let me write this value into here. Let me zoom a bit. Okay, this is our value in binary. After first shift, 1 will be entered from here. Let me shift this one. The above value will be same. The rightmost significant bit will be dropped into carry flag. Okay, this is our new value. Let me shift again. Another shift, the rightmost significant bit will be entered again, and the value is here. Let me divide this by this. The other value is this. Will be the second shift. And the third shift, rightmost significant value will be entered first. The other part is copied. The rightmost significant bit dropped into carry flag. This will be the result. Another shift, rightmost significant is here. All the value other than rightmost significant will be copied. This is the value. So we keeping this most significant bit, which is the signed operand in our register or values. We try to keep those values. So let's see what is happening. We put this value in here. Every operand is separated by 1. Shift arithmetic right by 1. The least significant value will be dropped into carry flag, which is already 0. This value will be shifted right by 1, and the most significant will be in again. So the value here, it becomes E6 1 1 1 1 0 1 1. Okay, the final value is F0. All of them is 1 except for the last two. All of them is 1 except for the last two. So this is shift arithmetic operation. At the end of this operation, we shifted by 4. The result is -4. So what just happened? Let me open a calculator for you. It was -56. Remember, we shifted 4 times. So shifting 4 times means dividing by 16. When we divide this value to 16, divided by 16. Why signed value is -4. We shift right by 4. The initial value, there's something wrong. The initial value CC, which is -52. Shift arithmetic right this value by 4 means FC. FC means -4, 13. Oh, what is wrong in here? Let me explain first what should it do. Shift arithmetic right and shift left, these operations are actually dividing and multiplying operation. For example, if you shift by 1, it means multiplying by 2. 2 to the power of shift means multiplying that amount of number. Let me write that value in here. For example, we have 5 in AL. I'm going to shift this value by 1. Shift left AL by 1. The result will be 5 will be multiplied by 2. So the result will be 10. Okay. As we can see, the result is 10. Shifting left is multiplying. Bu kısmı Türkçe açıklayayım arkadaşlar. Mesela onluk tabanda çarpma yaparken 10 ile çarpmak istediğinizde ne yaparsınız? Şöyle göstereyim. Elinizde sayınız var. Bu sayıyı 10 ile çarpın dediğimiz zaman ne yaparsınız? Sonuna 0 eklersiniz değil mi? Aslında yaptığınız şey bir hane sola kaydırıp sonuna 0 ekliyorsunuz. Yani shift ediyorsunuz. Onluk tabanda sonuna 0 eklemek 10 ile çarpmak demek. 16'lık tabanda sonuna 0 eklemek demek 16 ile çarpmak demek. İkilik tabanda sonuna 0 eklemek demek 2 ile çarpmak demek. Yani ikilik tabanda olduğumuzu varsayın. Mesela ne olsun? 2. 1-0. Bu 2 mesela arkadaşlar. 2. Bunu sonuna 0 eklediğim zaman ne oldu? 1 bit sola kaydırdım yani. 4 oldu. Yani 2 çarpı 2 oldu. 1 bit sola kaydırma 2 ile çarpma. 1 bit daha sola kaydırdım. Ne oldu? 8 oldu. 4 ile çarptım baştaki değerimi. 2'yi 2 bit sola kaydırarak 4 ile çarptım. 8 oldu. Bu 8 demek. 2 üzeri 3, 2 üzeri 2, 2 üzeri 1, 2 üzeri 0 hesaplamayı biliyorsunuz. Yani sola kaydırmak çarpmak, sağa kaydırmak da bölmek. Aynı şekilde 8 sayısını bir sağa kaydırırsanız 4, bir daha sağa kaydırırsanız 2, elinizde 2 kaldı. 2'yi bir daha sağa kaydırırsanız 2'yi 2'ye bölerseniz sonuç 1. Yani sola kaydırmak çarpmak, sağa kaydırmak bölmek. Aynı örneği buraya yazalım. Elimizde 2 olsun. 2'yi 2 kere sola kaydıralım. 3 kere sağa kaydıralım. Sonuca bakalım. Let's see the value of 2 by shifting left and right. Okay, when you shift 2 value, which is here, let's forget about the sign part. Our value is 2. We are looking for the AL. It is going to shift one by one. The first shift operation is done. It becomes 4. Shifting by 1 multiplies by 2. Another shift results into 8. Shifting by 2 means multiplying the value with 4. 2 to the power of shift is our case. So the value is now 8. I'm going to shift right 3 times, one by one, and we will see the 1 at the end of in here. I'm going to divide 8 by 2. The result is 4. Divide 4 by 2. The result is 2. Divide 2 by 2. The result is 1. So you understand that shifting left is multiplication, shifting right is division. Okay. Now we can use shift arithmetic right, shift arithmetic left also. We are going to use the signed value in here. We have 2. We have shifted 2 times. The result is 8. We have shift right 3 times. The result is 1. As we can see, the result is correct. But why? In our previous example, the CC value let me shift arithmetic right to, this should be hexadecimal. Yet the CC value, which is minus 52, divided by 4, because we divided by 3. No, divided by 4. It should be divided by 4. The result is 13. Okay, 13 is... Let's see what 13 is. Okay, we have shifted, right? It shifted correctly this time. 13. What was the error we are getting? Why we are not getting that error again? We write CC directly. 11001100 binary. This was CC minus 52. Okay. No, it's getting 13 again. We are not getting error. So this is what it's supposed to be. Okay. Any question? Any question, guys? So there's no question. Let's see the examples. First example. Write a program that multiply unsigned values 18 with the value of this memory address. We don't know what this memory address stores. We are going to multiply this memory address with 18. Okay, let's write this example. We have some value in 1000. Okay, let me ask this question first. How you can multiply with 18? Because we only do shifting 2 to the power of something. If you shift by 1, you multiply with 2. If you shift by 2, you multiply with 4. If you shift by 3, you multiply with 8. If you shift by 4, you multiply with 16. But if you shift by 5, you multiply it with 13, 32. Let me write it here. Let's say this is shift amount multiplication. Okay. If you shift 1 bit, the multiplication will be 2. If you shift 2 bit, the multiplication will be 4. If you shift 3 bit, the multiplication will be 8. 4 bit, it is 16. 5 bit, it is 32. It goes like this. But the question wants us to multiply it with 18. How can you multiply with 18 with shift instructions? Any idea? Yes, Salah. Salah is right. We shift by 4 bit, which is 16, and then 1 bit, which is 2, and then adding these two multiplication will result into 18. Let me write this in mathematical form. For example, we have a value times 16 plus 2. This is the mathematical value we are doing. We are going to shift by 16 and shift by 2, actually shift by 4 and shift by 1, add this result and make this multiplication. This is exactly the same thing with this, remember. Okay, but Utku has a question. Utku says, sarın tersi olarak sal var ama neden sar gibi uçtaki değeri eklemiyor? Sal. Let's open the Sol instruction. Yep, Sol exactly doing this. Aritmetik işlemleri yapmak için baştaki most significant bit'teki değerimiz eksi ya da artı olduğunu gösteriyor ya. Yani sağdaki bitin bir şey göstermediği için buraya kendisinin geri girmesi sadece sayıyı değiştirir. Hani aritmetik işlemde kullanılacak olan değeri tutmaya çalışmaz. Sağdaki most significant bit sign biti olduğu için onu tutmaya çalışıyoruz. Ama sağ taraftaki least significant bit bir anlam ifade etmiyor. Onu tekrar içeri sokmaya çalışırsan sayı değişir. Tamam. Utku? Umarım anlaşılmıştır. Okay. Let's write this example in emulator. We have some value in 1000 address. 1000 each address. I get those value into AL. I'm going to shift left. Multiplication is shifting left. AL with 4. Remember, we are going to shift left by 4 for 16. And then after shifting AL with 1. This is the wrong version arkadaşlar. If you shift by 4 and then shift by 1, this is exactly doing the shift by 5. This is exactly this. These two combine and the result is this, remember. So we are not going to shift by 5. This is multiplying with 32. That's why we are going to use the base value, which is in AL now, into BL. So AL and BL has the same value. Now I'm going to shift the base value with 4 and base value again with 1, and then add this 2 value, for example, into AL. And the question wants us to store the result into 1002 memory address and this value into 1002 memory address. But there's no value in 1000 memory address, so let's put some value into there. Let me put 2. Okay. 2 times 18 is 39. 36. So result will be 36 in 1002 address. 2 is in AL, 2 is in BL. AL becomes 20H, which is 32. BL becomes 4, which is 4. Then adding this 2 value will result into 24. 24 is actually 36 in decimal. So 2 times, let me write it in here. 2 times 18 is 36. Put this value into 1002 memory address. 36. Okay. Any question? No question. Second example. Write a program that divides signed value of this memory address by 4 using shift instruction. Which shift instruction make division operation? A little question for you. One of the shift is makes division in arithmetically. Which shift is that? Shift left or shift right? I want answers from you guys. Shift right. That's right. Shifting left is making your numbers bigger, multiplication. Shifting right is making your numbers smaller, which is division. Okay, we are going to divide by 4. By the way, there is no correct division other than 2 to the power of value. That's why you can only divide correctly by 2, 4, 16, 8, etc. 2 to the power of values. Okay, let's write this example. We have a value in 3000H. Sorry, we have a value in 3000H. Let's say the value is 20. I'm going to divide 20 by 4. The result will be 5. Get this 20 into AL, or we don't need to get into AL. We can directly shift right or shift arithmetic right. Which one? The question is here, how did you decide shift right or shift arithmetic right? Any idea? Some say shift arithmetic right. That's right, because the question says these are signed values. Okay, we are going to use shift arithmetic right. Remember, memory locations can also be used by 4. Is this correct? I'm going to divide 20 with 4. Is this correct? Or let me ask a question. In order to divide by 4, how many bits should I shift? Yes. In order to divide by 4 or multiply by 4, you have to shift 2 bits, not 4. So this means divide by 4. Let's emulate this. This is yep. This is it. We have 3014 divided by 4. The result will be in here. The result is 5. Any question? In order to divide by 4, we have to shift it to the right with 2 bits. Okay, I think there's no question. Let me move over to third example. Write a program that shifts the value of this memory address to the right. It is going to shift to the right until the value of 12th bit will be 0. Okay, we have a complex question in here. We are going to shift to the right until some value came. Let's put some value into this memory location. 1400. Let's say it's saying 12 bits, so it means we are going to use word PTR. We are going to use word 1400 and 1401. These two locations. Which value should I put there? Until it becomes 0. Okay. Let me put something like this. The value, another 0, 4, 4, 4, 4. This is some value. Let's see the value in memory location. This is F0, F0. Yep. We have F0, F0, 12th bit. Counting from 0 or 1, I don't know. Counting, I think, starts from 1. First bit, second bit, third bit, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is 12th bit. Yeah, 12th bit is already 0. So I'm going to change this value into something like this. Okay. So the value is F0, F8. Okay. And get this value into the register. AX is now that value. F8, F0. Actually, let's change this and it becomes F8, F8. Yeah, F8, F8. So 12 bit is here. The question says that write a program that shifts the value to the right until the value of 12 bit becomes 0. How can this bit can be 0 by shifting right? Which shift I'm going to use? Shift arithmetic right or shift right? Which shift? Which shift I need to use? Utku says shift right. In other answers, in other idea. Why not shift arithmetic right, Utku? You can write in Turkish. Neden shift arithmetic right değil? 12. bitimizin 0 olması için sağa doğru çevireceğiz. 12. bitimiz shift arithmetic right kullanırsak sürekli 1 ekler değil mi? Sol tarafa 1 ekleyip durur. 1 ekler, 1 ekler, 1 ekler. Hiçbir zaman 12. bit 0 olmaz. Biz de 0 olmasını istiyoruz. O yüzden shift left, shift right. Shift arithmetic right değil. Peki nasıl yapacağız? Biz o memorideki değerin ne olduğunu bilmiyoruz aslında. O değer gelene kadar döndüreceğiz. Yani elimizde bir döngü olacak. Şöyle açayım. Elimizde bir döngü olacak. Bu değer gelene kadar dönecek aslında. Şimdilik koşulsuz jump'a olan bir shift right var. A eksi komple 16 bitlik A eksi the whole 16 bit AX will be shifted right by 1 with SHR command. And after this shift, I need to check if the 13th, 12th bit becomes 0 or not. How that is going to happen? You can't answer this question now because you don't know the instruction yet. Let me open that instruction for you, which is test. We have an instruction called test, which is actually logical AND between all bits of 2 operands for flex only. It is like compare. It's making AND operation between 2 registers to memory. No to memory, register memory, memory register, register register, these combinations, and change the flex. and the result is not stored anywhere. It's like compare, but this time it is going to AND. So that's why I'm going to create a new variable like CX. Let me move over here. I'm going to write a number my number. This number, original number, will be tested with this number, and the result will be something. Zero flag will be affected. If the 12th bit becomes 0, the result will be, remember, ending is, both of them must be 1. The end truth table is only becomes 1, and both of them is 1. So there is no both of them is 1. The result is 0. So 0 flag is set. So I understand that 12 bit is 0. But for this case, the result is not 0. The result is 1. So 0 flag is not set. So I'm going to use this value with CX. I can use register. I'm going to test AX. It is in test AX with CX. And this affects the 0 flag. If the 0 flag is set, let's use jump 0, for example, to end. And let's say there is to end in here. If it doesn't set the 0 flag, the loop continues shifting right. Let's emulate and see if there is any error in this example. For example, how many times this example will shift to the right? Any idea how many times this example will shift to the right? 12th bit, which is in this case is this. How many times? Salah says 5, Utku says 5, Hüsam says 1. We are shifting right, Hüsam. These all values will be shifted to the right, so there are at least 5 1 coming from left. That's why Salah and Utku is right. We are going, it's supposed to shift right 5 times. Okay, CX value is here, which is 800. Put our original value into AX. Okay, we are in here. Let me open the AX in here. Look at the value in here. This bit that we are checking. By the way, let's open the flags. Look at the 0 flag. Shift right. Test with AX. 0 flag is 0. It is not jump because if 0 flag is set to 1, this is jump. The first shift is done. This is second shift. Test. Done. This is third shift. Test. Done. This is fourth shift. Test. Done. This is fifth shift. Test. And to the end. So this is our code. Until the 12th bit becomes 0, we shift it to the right. By the way, the result is 7C7. If the question asks that, I don't know. No, it's not asking. Any question? So we learned a new instruction, which is ANDing operation with test keyword. It ANDs these two variables, register, memory, whatever they are, and look at the zero flag. Actually, it changed 3 flag, sign flag, parity flag, zero flag. But currently we only look at the zero flag. By looking at zero flag, we write a simple loop. By the way, we can change this value into jump not zero. This is smaller version of our code. Yeah, 7C7. Another answer. Okay, the fourth question. Write a program that will find the nibbles of the value of 1000 memory address. The left side of the value will be written to the CH. The right side of the value will be written into CL. Let me explain this in text document. 1000H memory address is 8-bit. Remember, 8-bit value is something like ABH. The question wants us that CH and CL value should store the 0A, the left part of this value, into CH, and the right part of this value into CL. Okay. This is very simple question. You have to shift something, shift left, shift right, do something meaningful with CX or CL. It's up to you. I'm not going to cover this answer. I want you to try to find the answer on your own. Let me be more clear. The left side of the value will be into CH, the right side of it will be in CL. Yep, this is 8-bit memory. Nibbles means 4 bits. These are the nibbles, 4-bit value of the 8-bit 1000H memory address. The nibbles will be into 8-bit values of CH and CL. So the question is this is your homework. Try to find the answer on your own. I don't want to answer Salah for now. Trying to find the answer on your own. Okay, if there isn't any question about shifts, I'm going to end this session and this recording here. Any question, by the way? Let me ask again. Okay, I'm ending this record.